So I'll share with you guys my solutions to problems 14.1 and 14.2 here. So in 14.1, we're asked to show that lambda equal to 0 is the only real principal value of an anti-symmetric tensor. And they provide us that definition there. So we know that if the tensor W is anti-symmetric, then the diagonal is just going to be 0. So we can start building a matrix with that information. You can choose whichever 3 letters you want to throw into the 3x3 matrix for the axial tensors, or axial vectors rather. And I figure, or my thought process anyway, was just to start with the determinant. It's usually a good step or a useful step when you don't know where to go. So I started with that, calculated that out, and sure enough, that was the correct way to go. So we find out that lambda either equals 0 or it equals this complex number. So we know right there that lambda equals 0 is indeed the only real principal value of an anti-symmetric tensor. Moving on to problem 4.2, we're asked to show that the axial vector of an anti-symmetric tensor of this form is equal to the cross product here. So we know from our past knowledge of matrices, to build a 3x3 matrix out of 2 vectors, we need to multiply a column vector by a row vector. So we can build these 2 matrices here pretty easily out of our vector multiplications here. And just as a side note, we can see that this matrix here is just the transpose of this matrix here, which makes sense, but I thought it might be a good side note. Anyway, so knowing those 2 matrices, we can then subtract them to form this matrix. And then I'll get to this one in just a second. But moving on from here, I just formed a 3x3 matrix out of a definition for a cross product. That's all it is. So we can find the determinant of that here. And then that ends up just being a column vector in and of itself. So we can write that out here. Going back to this matrix right here, that is the definition from an outside source. I had a little trouble with this problem because, as you can see here, we end up getting the same thing we see here, just opposite sign, which bothered me because I couldn't quite figure out. I triple and quadruple checked my math, all seemed to be right. And as it turns out, if we go to the definition of an axial vector, it turns out that if we invert the direction of each vector, essentially, which is each row in this matrix, and invert just means to throw a negative sign on one of the components. It actually ends up being equal to this matrix here. Sorry if I'm going all over the place. I'm still trying to wrap my mind around how this all works. But essentially, putting this negative in here solves our issue with these 2 not lining up. So we end up finding that this vector here is equivalent to the axial vector here. And I've taken a advanced fluids class, so we used the axial vectors, which oftentimes correlate to vorticity a lot. And those axial vectors are these guys right here. And whichever way you decide to assign the negatives in this matrix, it should work out to be the same. So if I were to turn this positive and make these negative, and do the same thing up here and reverse the order, you should end up getting equivalent expressions for this axial matrix, whoops, and this one as well. So hopefully I made some sort of sense. It's still a little confusing to me as well, but maybe I explained it just well enough that you might understand a little bit better how that works. But thank you.